Discriminant analysis. This is a technique used to predict membership in two or more groups. Unlike multiple linear regression, discriminant analysis does not suffer from multicollinearity limitations between the independent variables. And it can also provide results despite the degrees of freedom issues. Now, I don't know how discriminant analysis solves the problem of independent variable multicollinearity, but I would be very wary about using discriminant analysis instead of ordinary least squares without doing significantly greater research on the technique. As well, the degrees of freedom problem is when you've got too few cases and too many variables, and this normally undermines the ability to make generalizations because it weakens significance tests. Normally, when you've got a very small number of cases, say 20 or 30, and you've got 3 or 4 variables, you're generally going to notice the degrees of freedom problem. When you've got hundreds and thousands of cases, and even if you have up to 10 independent variables, you're not really going to notice the degrees of freedom problem. But just looking at the T statistic table or the F statistic table, you can see how reducing the number of independent variables and increasing the number of cases improves the degrees of freedom problem, and therefore that doesn't improve the problem, it rather attenuates the problem, and that it gives you better significance. Now, in extreme cases, you could use discriminant analysis with 15 to 20 variables on only 10 cases. Now, again, I would be very careful about using discriminant analysis because it's not clear to me how it manages to produce that type of result. Also, although it can use categories in the dependent variable, I would be wary, again, of using it in the place of logistic regression. So let's proceed with an application. Get the data set. Graduate.save. This is a data set of whether a student will finish or not finish their PhD based on their letters, prior grades, their results in different GRE tests, their motive, their stability, their resources, their marital status, their age, how they interact with their peers, their apparent level of hostility, and whether they impressed the committee. So we have a lot of different independent variables here, a huge number. And the number of cases we have is actually quite small. It's only 50. Category is the dependent variable, and it means 1 if they finish their PhD and 2 if they did not finish their PhD. So here it's peculiar. We have only 50 students, and we have at least a dozen variables. So let's proceed with the analysis. Now, a grouping variable is a categorical dependent variable. Right? These are some terms you're going to come across in the results. A selection variable identifies a variable whose value will specify a subgroup for which an analysis is conducted, such as for only one category of completed. So you could just focus on those that completed PhDs or those that didn't complete, or consider both categories of the dependent variable at the same time. So you're going to have to define the range because when you enter the dependent variable, because this allows you to look at fewer categories. So it could be those that started a PhD and haven't finished, those that started and went through the process of terminating their PhD versus those that completed their PhD. So you could exclude one of those 3 categories. So let's get to the procedure. So we go to Analyze, Classify, then Discriminant. And here you can see a long list of independent variables. So into the grouping variable, we're going to put our completed, which is our first variable. And we have to define the range. So here we're going to have 1 for completed and 2 for not completed. And there could be more than 2 categories, but for this particular dependent variable, it's dichotomous. You either completed it or you didn't complete it. All the other variables will be inserted as independent variables. Now, you can have a selection variable where you look at the results, focusing on the different categories of a particular variable. we could, for example, take marital status. We can insert marital status here, and then we would attribute a value for the category of the selection variable that we're interested in. Right? But we're not going to do that. We're going to put all of the independent variables in here. We're going to choose the stepwise method because this is going to go through a process of iterations to then maximize the selection of the independent variables. And the selection method we're going to choose is going to be Wilks lambda. And we have to choose a criteria. And we're going to have as the entry criteria, and these are values I found in the literature as standard. I don't know why SPSS has these values as a default. Perhaps they have a different approach or philosophy. The manuals I consulted are both SPSS manuals and other manuals. So we go to statistics and we select means, univariate ANOVAs, boxes M, and unstandardized. And we click continue. Under classify, we're going to select under plots, combine groups, case-wise results under display, and summary table. And we click continue. And then under save, we're going to select predicted group memberships, discriminant scores, and probabilities of group membership. And now we're going to run it. So there's a lot of tables here, and in your notes I've listed the tables both by the heading and by the order in which the tables go to facilitate speed. Obviously, as this technique evolves in SPSS in the future, the table order will change. So the titles are still there. So table 2 is the group statistics. Now you're going to notice it's divided between finished, not finished, and total. And it's going to give you the mean, the standard deviation for each of the values of the independent variables. So for those that finished a PhD, what was their GRE score on the verbal test? Right? What was the average score? Versus those that didn't finish. What was the score on verbal? And we can see that those that finished versus those that didn't finish did slightly better. So you can see that it has it for all the different independent variable values for the categories of the dependent variable. Table 3 is a focus on Wilks lambda, and it's the test of equality of group means. Now lambda is typically stronger as its values go from 1 to 0. So in this case, smaller is better in the evaluation. And it indicates the effect of the independent variable upon the dependent variable. The F significance test is conventional. So you interpret it the way you normally do. And it's a test of whether there's a false positive. A probability of 0.05, 5%, is good. A high score is bad for the significance. So this tells us roughly which are the independent variables that are significant, which are not. And we would rerun this test and exclude those independent variables that had a poor result on the Wilks lambda and had a lack of significance in the F statistic. So let's go now to table 6, which is the stepwise statistics. So here we have stepwise statistics, variables entered and removed. Again here, the criteria is Wilks lambda, which is the statistic. Lambda represents not one variable here, but it's actually an evaluation of the multivariate model and the variable within the multivariate model. So we have here a list of the independent variables which best explain the categories of the dependent variable. So it's thought that these are the independent variables that you should have in a model. And this was arrived at by using the Wilks criteria in the stepwise method. So rather than just simply entering the values once, there was an algorithm in discriminant analysis which reran the model over and over again, optimizing it until it settled on these being the best and significant independent variables that should be included in the model. So let's go now to boxes M, and we can see it up here. This is table 5. Now this is a test of the multivariate normality of the data, which is important because discriminant analysis still assumes normality. A good result consists of a high value of P. So P should be greater than 0.05, which it is. And this is, again, counter traditional usage. So as we get into these more obscure approaches, you have to be wary that the significance tests might have to be interpreted in the opposite direction. Now, the low value, or a low value, if there was a 0.05 or less value in the significance, could be the result of the absence of normality in some of the variables, like gender. Gender is clearly not normally distributed because it only has two categories. Now we're going to jump to table 14. Okay, we're going to go to the unstandardized canonical discriminant function coefficients. And it's sort of near the enters. We'll just sort of count our way through there because it's sort of confusing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Here we go. Canonical discriminant function coefficients. These tell us what are the best independent variables. So what I've done is I've taken these and I've taken some other variables that I thought had good results from the previous table. And what I'm going to do is rerun the model with these improved variables. Okay, so let's go do that. Go to Analyze, Classify, Discriminant. And here I'm only going to include the variables that I have here in the notes that indicate that the results were good with those variables. So I'm going to throw out all the independent variables first and then reinsert them as I find them to be having a strong Wilks significance. And so the first result, the first rather independent variable is going to be gender, which I will insert. GRE area. Which is GRE area GPA. So it must be, yeah, here we go, GRE area, there we go. GRE verbal, the second letter. It's always peculiar why the second letter here is important. These are sort of an arbitrary data set, but it's perhaps the first letter was done in a rush by the primary supervisor because they've got too many people supervising, where the second reader is perhaps somewhat more relaxed and has fewer responsibilities. Here's the motive. Why is the student there? Are they there for status? Are they there for intellectual curiosity? Do they have the money? Some U.S. universities are incredibly expensive. Age, and whether just generally in the process of the interview they were impressed with the results. We would run this again, and you would redo all of the examinations. And so here you have Wilks lambda, which assesses these variables, and some of them are still not optimal. So we're going to, be careful that we're not stuck in this lower, the second test that we ran. We're going to stick with the first test. So let's go now to table 10, which is going to give us the eigenvalues. So here we have the eigenvalues. An eigenvalue of greater than 2 indicates a strong discriminant solution. So we have that. Okay, so some of these variables are actually very useful. That's the conclusion of this. Table 11 is Wilks lambda, and it uses a chi-square distribution. And indicates whether the discriminant procedure created a successful solution. Here, probability of 0.05 is an indication of a good discrimination. So here we have a conventional interpretation of a chi-square and its significance test. Table 12, we have here the canonical correlation. Yep. Canonical, standardized canonical, and it's rated from 0 to 1. 0 is low, 1 is high, and indicates the strength of the discriminant solution. Right, so these all have some moderate effect on the dependent variable. So let's go now down to table 18, which is case-wise statistics. All right, so here we are. So this looks at the different cases. It looks at the actual group they're in, which, if you recall, is the observed status of a case. And this is the predicted group, which is the prediction made by the model. A double asterisk indicates a misclassification. So there's 1, 2, 3 misclassifications here. One in which a student did not complete the PhD, but it was predicted they would, and another two cases where they did complete the PhD, but they were predicted not to. So we have different sections here. P, D is larger than small d, G is equal to G. It's for the given case, it's the probability of being inside that group. So it gives us a probability of the group that they were predicted to be in, whether it was correct or incorrect. For G is equal to G, D is equal to D, the second highest group, for a given case, given its membership, what is the probability of its discriminant score? So here it's an assessment of whether the discriminant score that it was attributed is correct. Now we have also the second group. Here, there's a second group here. What is the second most likely assignment of the case if more than 2 categories are available in the dependent variable? So here we don't. We only have 2 categories. So this is sort of meaningless. But if we had 3 categories, this here would then indicate the next most likely group membership. And finally, we have here the classification results, which is table 19. It's the overall classification between the observed and predicted. And if you recall, this is original or actual observed membership, and this is the predicted group membership done by the model. So this is discriminant analysis. Use it very carefully. This lecture is mostly so that you're able to consume any study using discriminant analysis. I haven't taught you enough here to be able to use it on your own carefully.